Recall that our goal is to recover a curve from its function field. And we've said that one way to do so is by viewing points on the curve as rings. To every point on an irreducible curve, we can associate a subring of the function field, namely the ring of regular functions at the point. We then ask, does this ring determine the point P uniquely? That is, if the local ring at P is equal to the local ring at Q, does that mean that P and Q must be the same point? Now, since this is merely a local question, let us assume that C is affine with coordinate ring A. We want to consider this case because in this case, the local ring has a very nice description. It's just gonna be the localization of this coordinate ring at the ideal functions vanishing at P. Recall that this is a ring obtained by inverting all the regular functions that do not vanish at P. In this case, our question becomes, if these two localizations are the same, does it mean that P equal to Q? Actually, we can go further and turn this into a purely algebraic question. This is because we have assumed at the beginning that K is algebraically closed, so we have the null cylinder, and thus P and Q are uniquely determined by the ideals of function vanishing on them. In particular, if the ideal functions vanishing on P is equal to the ideal functions vanishing on Q, then P and Q must be equal. So let us now try to answer this question. Is it true that if these local rings are the same, then these maximal ideals must also be equal? Note that we are viewing these local rings as subrings of the function field of C, which in this case is the field of fraction of A. Alright, so let us prove this. Actually, let us prove something slightly stronger. We'll show that if this one of these local rings contains the other one, then the two maximal ideals must be equal. Observe that by maximality of these ideals, it suffices to show that one of them contains the other, and that's what we'll do. So by contradiction, let us assume that there is some element f lying inside this ideal MQ, but not in MP. This is a regular function that vanishes at Q, but not at P. Well, now because f does not vanish at P, 1 over f is a regular function at P. But by our hypothesis, any function that is regular at P must also be regular at Q. Thus, the local ring at Q contains both f and 1 over f. In other words, f is a unit in this local ring. And that's a contradiction because a proper ideal cannot contain a unit. Thus, we see that if the local ring at P is contained inside the local ring at Q, then the maximal ideal at P must contain the maximal ideal at Q. In particular, they must be equal. Thus, we have established that in the case when C is affine, then the local ring at every point P of C determines P uniquely. Now, what about the case when C is not affine? Well, even if C is not affine, one will always be able to find an open affine subset of C containing both P and Q. And these local rings can be computed in terms of the coordinate ring of U, so this brings it back to the affine case. Thus, we have established that for a point P on a curve C, the local ring at P determines P uniquely. You may observe that actually we never use the hypothesis that C is a curve. We never use the fact that the dimension of C is 1. That is true, and indeed, every point on a general quasi-projective variety is uniquely determined by its local ring. So why then are we focusing on the case of curves? Well, remember our original goal was to go in the other direction. We want to start from a function field big K and construct a variety X such that the function field of X is equal to big K. In general, such an X is not going to be unique, but it is unique in the case when big K is of transcendence degree 1 over little k, and if we require X to be non-singular. In the case when big K is a function field of transcendence degree 1, then for a certain type of subrings of big K, there always exists a certain variety X such that this ring is the local ring at a point of X. That is the idea underlying the construction of this non-singular variety. Thus, our next question is, which subring of big K can be realized as the local ring of some non-singular variety? And for that, we need to understand the algebraic characteristic of the local ring at non-singular point on a curve. That will be the topic of the next video.